Okay, good evening, everybody. Professor Ayorinde welcoming all of you to the first organic chemistry lecture for the fall 2013 semester. And I'm sure that most of you enjoy your summer vacation, and you guys are happy to be back at Howard. Is that correct? I see a lot of happy faces here. Okay, so today we are going to start a journey of organic chemistry, during which we are going to study organic chemistry, of course. And during the course of this journey, we will be studying about the different molecules that make up the organic molecules. But before we start the session, let me simply take a few minutes here to go over some of the housekeeping information with regard to the administration of this class. Okay. How many of you have gotten a chance to see the syllabus? Okay, very good. So most of you have seen the syllabus. Just to refresh your mind for all of you who have seen, and those of you who have not, I will go over a few of the items that are very important in that syllabus. Of course, every aspect of the syllabus is important. Okay, my office is in room G15 of the chemistry building. G15 of the chemistry building. My office hours on Tuesdays and Thursdays from 1:30 to 3:30 p.m. Now, that does not mean that that is the only time you can see me. If you wish to see me and you cannot see me during those office hours, just send me an email and request for a meeting. I generally come in here Monday through Thursday in the afternoon. So anytime after 2 p.m., Monday through Thursday, if you want to request a meeting, that would be fine. I do not come in on Fridays. Okay. I do not come in on Fridays. Okay, the textbook that we are going to use is McMurray, which is this book right here. I will also advise you that you need to buy the companion solution manual, which is also by McMurray. In addition to that, there is part of the package, the textbook package, what we call the online web learning software. And the acronym is OWL. We are going to use OWL for your homework assignment every week. So every week I will assign a set of problems for you, and then I will also let you know when the deadline for the completion of the problems will be. Okay, so the OWL will be our homework assignment and also will be the online quizzes. Okay. The prerequisite for this class is Chem 003-004. I'm sure most of you or all of you have already successfully completed those courses. Okay, with regard to performance evaluation, there will be several quizzes. As you can see here, we are going to have quizzes worth a total of 100 points. And some of those quizzes will be in-class quizzes. In other words, whenever you come to class, there could be a quiz at any given time. Okay. In addition, there will also be the online quizzes in which we are going to use OWL, the one I told you earlier. Okay, both the online quizzes and the in-class quizzes you get a maximum of 100 points from both of those set of quizzes. The in-class quiz is worth 12 points each, and the online quiz is worth 5 points each. As you can also see here, we have 50 points for class participation, and there are many ways in which you could earn 50 points towards class participation. So I want you to take a closer look at the syllabus. You will find that information in the syllabus. We are going to have 4 in-class exams, each one of them worth 150 points. And I will be dropping one of those exams. And finally, we have a final exam which is comprehensive, and that exam I believe will be on December 10. For the seniors, your final will be December 4. Okay, so for the seniors, that means you really have to do a lot of work at the end of the semester, because you are going to have a series of exams almost back to back for the seniors. Okay, with regard to your letter grade at the end of the semester, you will be competing with your colleagues in this class. As you can see here, A will be 95% of the highest score in the class. The maximum score you could score will be 1,000 points. So let's say that the maximum score was 900 points. That means 95% of 900 will be A, 85% will be B, 75% will be C, 50% will be D, and less than 50% will be F. It is my hope and expectation that nobody in this class will be earning an F. Okay. Okay, the days of the exams, I told you earlier, we have 4 exams, in-class exams. The first exam is on Thursday, September 26th. That is the first exam, which is almost about 4 weeks from today. Of course, the last exam is on Thursday, December 5, which is the last day of class. Okay, and so the seniors will be taking the 4th exam on December 5, and also will be taking the senior final exam on December 4. Okay, with regard to student code of conduct, okay, I want to refer all of you to the Howard University student reference book. All of the information regarding the student code of conduct will be you'll find on that reference manual. But in addition to that, I do want to call your attention to a few other items that I want to make sure that you are aware of while you are in this class. Whenever we are taking an exam, I do not want anybody to listen to any audio device, because since all of my lectures, all of my past exams, everything are on YouTube, and they are also on all kind of recordings, so I do not want you to be listening to my lecture while you're taking the exam. So, okay, so no audio device while you're taking the exam and quizzes. Also, during the exams and quizzes, no smartphones and no scanning devices. Okay. I also do want to let you know that anytime you take an exam, I make a copy of all of the original exam before I give them back to you. Okay, so I just want you to know that. Okay, finally, with regard to the American Disability Act compliance with the ADA guidelines, if there is anybody in this class who needs some special assistance, Of course, you have to go through the dean of the special student services. They have to certify that you need special assistance, and then you will get a letter from them to me. Make sure that you do that at the beginning of the semester. I will not entertain any letter at the end of the semester saying that, well, I have this problem and I just didn't tell you. No, that will not work. Okay, if there's any problem right away, you need to go to that office, and then they will send me a letter so I know what to do to help you. Okay, is there any question before we go to today's presentation? Of course, you could always come to me if you want further clarification on all of these items that I just outlined to you. Yes, that's Gamble.
Yeah.
Devin Gamble. Okay, very good.
Maybe I'm misunderstanding this, but so we need 95% of the total possible points in order to get an A?
No. 95% of the highest score in the class.
So the highest score someone in the class gets, we need 95% of that?
Yes.
Okay, thank you. And on the OWL, it seems like there's more than one version of your class on OWL. I'm not sure which one I should sign up for.
Okay, the one you sign up for will be the one that says, I believe it says, Fall 2013 Ayorinde. Okay, Organic 1. Okay, make sure it says Fall 2013.
Yeah, Ayorinde.
Okay, Ayorinde Organic 1.
Okay. Thank you.
Is that clear?
Yes.
Okay. Any other question? Okay. Okay, now, so we are going to start, like I told you before, we are going to start a journey of organic chemistry. And hopefully during the course of this journey, we are going to learn a lot about organic chemistry. Today we start with the introduction to organic chemistry. Specifically, we are going to discuss structure and bonding. You will find that most of the topics and concepts that we are going to discuss today, most of them we've done already. So today's session is essentially almost like a review of what all of you have already done in general chemistry. So therefore, this is just to reinforce some of what you already know. So during the course of this chapter, we are going to discuss the uniqueness of carbon, electronic configuration, valence electrons, valence bond theory, hybridization, and throughout the course of this lecture also, we are going to begin to introduce you to the different ways of writing organic chemical structures. On this next slide, like most of my lectures, what I generally do for each chapter, I have a list of items that I refer to as learning outcome objectives. In other words, this list of items you should use as a study guide, used for studying for this chapter. For example, upon completion of this chapter, Hutchinson, can you read for us item number 5? What does 5 say?
Write the number of valence electrons of atoms that are relevant to this course.
Very good. In other words, upon completion of this chapter, thank you. Upon completion of this chapter, you should be able to write the number of valence electrons of atoms that are relevant to this course. Right? Okay, number 6, Kira, can you read number 6 for us? Wait, I think I have to. Is that you? Was that you reading? I must have 2 killers here. No, go ahead. No, that's fine. Yeah, go ahead. Did I say Kayla, right? Did I say it right or wrong? K-A-Y-L-A.
Mm-hmm.
Oh, I'm sorry. Okay. I was saying I was looking at somebody. Yes, go ahead. Yeah, read number 6 for us.
Identify atomic orbitals containing electrons that are used for bonding. Sounds bond theory.
Okay, thank you. In other words, upon completion of this chapter, you should be able to do the item on number 6. In other words, all of these items here, you should use them as a study guide for studying for the content of this chapter. Okay, now let us now begin to take a look at carbon atom. By the way, if I ask you, what is organic chemistry? Does anybody have an idea? What is, yes?
It's the study of carbon and carbon-containing compounds.
Okay, study of carbon-containing study of carbon-containing compounds. Very good. That is correct. Now that organic chemistry is the study of carbon-containing compounds. In other words, those molecules that contain carbon atoms. Some people also say organic chemistry is also the study of compounds that contain carbon atom and hydrogen atoms. That is also correct. Okay, so in essence, therefore, we are going to be studying the chemistry of those molecules that contain carbon atoms. Now, if you take a look at this slide, I have a series of organic molecules that will show you examples of organic molecules. And also, I want to use this to demonstrate the uniqueness of carbon atom. Now, if you take a look at this here, you have this molecule here we call methane. This here we call ethane, propane, butane. These are all of the components of your cooking gas. If you notice in each one of these cases here, you have a carbon atom in there, right? Okay, you also have, attached to the carbon, in some cases you have hydrogen attached to them. So these are examples of organic molecules. Now, while we are looking at the structures, I want to use this opportunity to also begin to introduce you to the different ways of writing organic molecules. You look at these 4 structures here. These 4 structures here, what we have here is what we call line bond structures. Sometimes we refer to them as calculate structures. Calculate structures. In other words, in the calculate structures, what are we showing you? We are showing you each one of the atoms that are present in the molecule, and we also show you the bond between each pair of atoms. In other words, here we have carbon attached to hydrogen. Okay? Here we have carbon attached to carbon. Carbon attached to hydrogen. Okay? So in the calculate structure, you show all of the bonds that are present in the molecule. So that is what we call the calculate structure. Now, I could also write this same structure in a different way. For example, for this one here, I could write this CH4. This here, the ethane, we could write CH. See this part of the molecule here. This part of the molecule here, I could focus on this part of the molecule here. That is CH3. Okay? And then there is, that CH3 is bonded to another CH3. Then CH3. Okay? The same thing on this side. The same thing on this side. Okay, what do I have if I want to write this? This, by the way, this would be called the semi-condensed structure. This would be called semi-condensed structure. Now, if I want to write this here, the propane in a semi-condensed structure, what do I do? What do I do? I look at this part of the molecule, right? That's a CH3, carbon attached to 3 hydrogen atoms, right? Becomes CH3. Then I take a look at this part of the molecule right here. Okay, that becomes a CH2. And then finally this part of the molecule right here. And that's a CH3. This is also a semi-condensed structure. Now, supposing I want to write the semi-condensed structure for butane, for this here, right here. How many CH3 do you think I will have? At both ends of the molecule, right? Is that correct? Okay. So therefore, if I want to write the semi-condensed for the butane molecule, that will become CH3, CH2, CH2, and CH3. Okay. So far, so good, right? Now, I could further write this here in a different way, in which the molecule will be completely condensed. Instead of writing the bond between this carbon and this carbon, here, 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 I could remove that. I'll simply do this. CH3, CH2, CH2, and CH3. This we call the condensed structure. That would be the condensed structure. In other words, I did not show in the condensed structure, you do not show any of the bonds. Now, I could further condense this. Notice what I've done here. This right here. You have a CH3, CH2, CH2, CH3. I could write it in a different way. Supposing I want to make things even a little easier for myself, I will simply do this. Okay? Now, this here is what we call the skeletal structure. This is called the skeletal structure. Now, in the skeletal structure, what do you have? The end of a line is a carbon atom. Okay? The end of a line is a carbon atom. Let me take this out. Okay? The end of this line right here is this carbon atom. Okay? Now, in the skeletal structure, you do not show any of the atoms. If the atoms in the molecule are carbon and hydrogen, you do not show them. Okay? Here, the end of the line is a carbon atom. The intersection of two lines is a carbon atom. In other words, this right here is this CH2 right here. This intersection right here of two lines is a carbon atom, which is this here. And the end of this line also is a carbon atom. Now, what does this tell us? If you look at this molecule here, the one feature of carbon atoms is that carbon atom will always need 4 bonds. Okay, keep that in mind. Most important, carbon atom always needs 4 bonds in order to form a stable molecule. Okay, carbon always needs 4 bonds in order to form a stable molecule. Okay, what do we have here? This carbon here is bonded to 4 hydrogen atoms, right? About this carbon here, how many hydrogen atoms is it bonded to? 3, then bonded to a carbon atom, right? So it is bonded to 4 other atoms. The same thing with this carbon here. So carbon must always be bonded to 4, and must always have 4 bonds. Keep that in mind. Okay. Now, keeping that in mind, if we write a skeletal structure in which we do not show the hydrogen, and then we tell you that the end of the line is a carbon atom, right? Okay, we know that this here, the intersection here is a carbon atom. So what does that tell you about this carbon? What is it attached to right here? It must be attached to hydrogen atoms. Okay, if we do not show any other atom, if we draw a skeletal structure and you do not see any other atom, you have to assume that the missing atom must be hydrogen atoms. Is that clear? So therefore, since we do not show any other atoms here, there must be 3 hydrogens here. Okay? How many hydrogens here? How many hydrogens here? How many hydrogens here? Okay? Therefore, in the skeletal structure, you only show the lines, the bonds. You do not show the carbon. You do not show the hydrogen. Okay? Now, supposing I ask. So the point we made there, before I go to the next point, the point we made there is carbon atom has the capability to bond to other atoms. Okay, that is one feature of carbon. Carbon has the capacity to bond to other atoms to form stable molecules. Now, supposing I have this. Supposing I have this. And I ask you to give me the molecular formula for this molecule right that I've drawn here. Can anybody give me the molecular formula? This is the skeletal structure. Okay? Based on what we just said so far, what would be the molecular formula for this compound? Let's start with the carbon. Let's start with carbon. C? C what? How many? How many carbons? I can't hear. Oh, okay. Let me see. Okay, let me. I see. Okay, I see why you say 5. Let me take this. Okay, how many carbons? 6, exactly. So you have C6. How many hydrogens? 12, exactly. 12. Because each one of these carbon here, in order for carbon to have 4 bonds, must be 2 hydrogen atoms, right? Okay, so therefore, this is C6H12. And that would be the molecular formula for that molecule. Now, supposing I ask you, I draw this molecule here, and I ask you to give me the molecular weight of this compound, right here. What would be the molecular weight of this compound? What is the first thing you do? You draw the molecular formula, right? Then from the molecular formula, you calculate the molecular weight, right? So what will be the molecular weight of this compound here? You have the formula is C6H12. Okay? Atomic weight of carbon is 12. 6 times 12 is what? 72. So that is 72 plus atomic weight of hydrogen is 1. 12. So you have. So that is 84. So this molecule is 84 grams per mole, right? Just from based on the formula. the skeletal structure that I've given you, then I say, give me the molecular weight. You should be able to do that. Now, okay, so far we know that carbon will bond to other atoms to form stable molecules. Now we also know, take this out. Take a look at this molecule here, nicotine. Nicotine that you find in your cigarette, right? What do we have in this molecule? Okay, this part of the molecule, what is this here? What atom is this? Carbon, okay? Notice in this case, sometimes you may have a structure in which we are combining both the skeletal structure and the semi-condensed structure. That is also possible. So this here is almost showing you both skeletal structure and semi-condensed structure, because you have CH3 right here. Now, so you have this. Anytime you want to write a skeletal structure and you have other atoms, which we call heteroatoms, heteroatoms are those atoms that are not carbon and hydrogen. Okay, in other words, oxygen is an heteroatom. Nitrogen, heteroatom. Okay, so anytime you have an heteroatom in a molecule and you want to write a skeletal structure, you got to show that heteroatom. Okay, for example, if I want to do this, okay, because I have nitrogen in this molecule, I have to show the nitrogen, even though I am writing a skeletal structure. Now, if hydrogen is attached to an heteroatom, you must show it. And that is why I show the hydrogen attached to nitrogen here. Okay? Okay, so now, let us come back to nicotine. So what do we have here? See, nicotine, we have carbon atom, right? We have carbon atom, carbon, nitrogen. See what is happening here? Carbon is bonded to nitrogen. And you have double bonded to nitrogen. So therefore, another unique feature of carbon is the ability of carbon to bond, multiply to other atoms to form stable molecules. In other words, carbon can form multiple bonds with other atoms to form stable molecules. That is another unique feature of carbon atom. Okay? Not too many other atoms can do that. Carbon can bond, multiply to other atoms in order to form stable molecules. And that is what you have here. You have this carbon here. This carbon here is bonded to nitrogen. It's a double bond to nitrogen. Okay? And carbon can also bond, do a multiple bond to itself. Look at this carbon here. That's a double bond to itself. So that is another unique feature of carbon atom. Okay? In all of these cases, what is constant is carbon has how many bonds? 4. In all of these cases, what is constant is carbon has 4 bonds. If you look at this, if you take a look at this carbon here, if you take a look at this carbon here, right? You have this bond to this carbon, right? You have this bond to this carbon, that is 2. Then you have double bond to this other carbon, that's a total of 4 bonds. So carbon, in order to form a stable molecule, must have 4 bonds. If you do not learn anything in organic chemistry, that much you say, yes, I have learned in organic chemistry. Okay, now, so now let us take a look at other this molecule here, virus, which is a pharmaceutical drug. Look at oxygen atom. Okay, look at oxygen atom. This is also a skeletal structure. This oxygen atom, how many carbon atoms is it bonded to? How many? 2 is bonded to this and this. This is a carbon atom right here. Right here. Okay? And this oxygen here is also bonded to a carbon atom right here. Keep in mind the intersection of 2 lines. In this case, this line here, this and this, that's a carbon atom. Okay, so this carbon here is also has 4 bonds. Okay. Okay. Of course, this other molecule here, we see here, carbon bonded to oxygen, carbon bonded to oxygen. The point we made here is carbon is capable of bonding to other atoms to form stable molecule. It is also capable of forming multiple bonds to other atoms and to itself to form stable molecules. Okay? And so far, we're also giving you different ways of writing organic chemical structure. We're giving you the line bond structure, give you the semi-condensed, we're giving you the condensed, and we're also giving you the skeleton. Very often we use a combination of all of this. Okay. Okay, on this slide here, simply just reiterate some of the things that we have just been discussing, some of the uniqueness of carbon. Ability to form stable bonds with most elements. Ability to form stable bonds with itself. Carbon can also form stable bonds with itself. Ability to form stable multiple bonds with itself also. Ability to form stable multiple bonds with other elements. These are all of the unique features of carbon atom. And finally, which is very important, the ability to form stable complex molecules with other elements that have essential biological activities, which is essentially what we have here. See? All of these here, these are pharmaceutical drugs. So therefore, why do we study organic chemistry? Because organic molecules are very important. Okay. Now, before we move on, I would let you know that studying organic chemistry really is very easy, because we, as organic chemists, we only deal with a few atoms in the periodic table. So you don't need to worry about most of the other atoms in the periodic table, only a few of them. Okay, for example, for the most part, the elements that are of interest to us will be, of course, we have carbon atom here, nitrogen, oxygen, fluorine, phosphorus, sulfur, fluorine, bromine, iodine, of course, hydrogen, and maybe once in a while boron and silicon. So these are all of the atoms that are of interest to the organic chemist. So you don't really need to bother yourself so much about the rest of the periodic table. If you want to do that, that's fine, you know. But for the most part, we are going to concern ourselves with the chemistry of carbon in relation to these other elements. Now, what I want to do now, okay, this year you guys should be able to read this on your own in terms of the history of the evolution of organic chemistry, how initially organic chemistry used to be thought of as the chemistry of those compounds that were derived from nature. Those are close to 200 years ago. But the organic chemistry has evolved to the point now when you said it was exactly the study of carbon-containing compounds. That is what organic chemistry is today. So anyway, but you are free to go in your book and read the history of the evolution of organic chemistry. So what I want to do now, since we are going to be dealing with organic molecules most of the chemistry that we are going to be discussing will be chemistry at a molecular level, okay? Chemistry at a molecular level, in which you have atoms bonding together, forming molecules. And so we are going to be looking at these molecules. So to do that, let us begin to also take a look at the basic unit of all the elements or all the atoms. I'm sure this is a review to all of you, but I thought it is important that at least sort of bring this back so that you begin to relate to, when we get to further down the line, you begin to relate back to the fundamental structure of elements, in which we say that all atoms have essentially what we call a nucleus, right here, nucleus right here. And the nucleus consists of the proton, which is positively charged, and the neutron, which is neutral. Surrounding the nucleus, we also know we have electrons that surround the nucleus. And those electrons are negatively charged. So what you have here is, since for the most part, we have the same number of electrons as we have the nucleus, the atom will be electrically neutral, because you have the nucleus is positively charged, the electrons surrounding the nucleus are negatively charged, and you have the same number of you have the same number of protons in the nucleus as you have electrons. So therefore, the atom is electrically neutral. So what does that mean? If I remove, say I have a bunch of electrons surrounding this nucleus here, I remove one electron from here, I take it away. What do you think is going to happen to that atom? Will it have a charge? Will it have a charge? If I remove one electron from it, will it have a charge? Yes or no? Yes. And what will be that charge? It will be positively charged. Because since I remove one electron from it, and that is the only thing that is making the molecule electrically neutral, now we don't have the balance of proton and electron. So therefore, that atom will be positively charged. That's important when we get to chemical reactions. Okay, so therefore, we say we have the nucleus. Surrounding the nucleus, we have a bunch of electrons. But these electrons are not just moving all over the place. Okay? These electrons, you can only find them in specific arrangement around the nucleus, in a specific region around the nucleus. You know, in other words, it's not just electrons just moving around. There's a specific area around the nucleus in which you find them. And this specific region around the nucleus that you could find the electrons are what we refer to as orbitals, atomic orbitals. Electronic orbitals. And these electronic orbitals also have specific shape. We have what we call the s orbital. The s orbital is round. In other words, any electron within the s orbital is going to be within that space, which is round, it's circular. Okay? And that is what you have here. So the s orbital is circular, is round. Any electron within that space is going to be within that. In other words, will be equidistant from the nucleus. No matter where it is, it will be the same distance to the nucleus because it is round. Now, we also have another set of orbitals, another region in space surrounding the nucleus, which we refer to as the p orbital. And the shape of the p orbital, like dumbbell shape, okay? So that is the p orbital right here. Now what does this mean? For the most part, the orbitals that will be of interest to us as organic chemists will be the s orbital and the p orbitals. Okay, we don't need to worry about the d orbitals. Now, so you have these electrons either in the s orbitals or the p orbitals. Now, we also know that the p orbitals, they have some angular feature to them. In other words, the p orbital, because of the shape of the p orbital, they could be in 3 different directions. They could be in the x direction, in the y, or the z. Okay? So now you have the different p orbitals. Because of the shape of those p orbitals, they are directed in the different direction in space. You have what we call the px orbital. You have the y orbital, in which it's going in vertical direction. The x, which is the horizontal. And the z, of course, which is perpendicular to both the y and the x orbital. So what do we have here? So we have s orbital, we have the p orbital. The p orbital, you have 3 types of p orbitals, in which you could have this electron just floating around. Now this is very important. Now if I ask you, keep in mind we say the s orbital is spherical, is round. If I ask you, what would be the relationship between the p orbital and the s orbital in terms of the angle between them? Would the p orbital be perpendicular to the s orbital? Keep in mind the p orbital will be here, somewhere here. Change my pen. This is the s orbital here. So the p orbital will be somewhere here. Will it be perpendicular to the s orbital? Yes or no? Of course, it will be. It will be. The p orbital, you will expect the p orbital to be perpendicular to the s orbital. That is very important when we get to bonding. Okay? Okay? So therefore, so you have this here, this is p, and of course this is your s. So we expect, yes, right.
Is that FP in any direction? It's all perpendicular?
Yes, yes, it will be, no matter what direction. Because if it is in the x-axis, it will also be perpendicular. You know, you are dealing with a circle. Okay. No. Okay, so anyway, so we have the s and the p orbitals. Those are very important. What time do we have left? Oh, wow. We've got plenty of time. You guys are going to hear me say a lot about plenty of time. Anyway, so it's just about 7 o'clock. So we still have about 30 minutes. Okay. So where are we going with this? So now we know these electrons are in the s orbital and the p orbital. Yes. Say that again. The electrons.
Did you say that the relationship between the s orbital and the p orbital is that it lies perpendicular?
Yes, yes, they are perpendicular to each other. Yes, yes. Okay. Now, in addition to that, we also know that these electrons, in addition to being in a specific region in space surrounding the nucleus, you also have different energy levels in which you have these orbital, electronic orbitals. We have what we call the first energy level. Here we call the first shell. Okay, if you think of this as energy, in other words, The first shell is the lowest energy level, closer to the nucleus. The second shell, second energy level. Now, in the first shell, you only have one orbital, and that is the s orbital in the first shell. Okay? In the first shell, you only have one orbital, and that is the s orbital. Now, in the second shell energy level, you have two types of orbital. You have the s orbital and the p orbitals. Okay. And if you also notice this, each one of these here represents an electron. Each one of those orbitals will take a maximum of 2 electrons. And that is what this is depicting right here. Okay. So you also have the s orbital within the second energy shell and the p orbital. Okay, the s orbital being a lower energy orbital, and the p orbital being a higher energy orbital. Now you have the third shell energy level, in which you now have 3 types of orbitals. You have the s orbital, in this case we say the 3s orbital, the 3p orbitals, and the 3d orbitals. Keep in mind once again, each one of these orbitals will take a maximum of 2 electrons. Okay? So now you now have what we now have referred to as electronic configuration. We will now take a look at each carbon atom or each atom and begin to now write the electronic configuration. We begin to write where will those electrons be. Okay? So let us take for example. Let us take, for example, carbon atom. Let's take carbon atom. This here, for those of you who are familiar with the periodic table, these numbers here, 5, 6, 7, 8, this represents the number of what? Protons, exactly, very good. And the number of protons is also represent the number of what? Electrons. Okay, and we refer to this as atomic number. Okay, so we call this atomic number. So the atomic number gives us the number of protons in an atom. It also gives you the number of electrons in an atom. Okay, so there you have, for carbon atom, how many electrons do you have surrounding the nucleus of carbon? How many electrons? 6. About nitrogen, how many electrons? 7, right? About oxygen, 8, fluorine, 9, neon, 10. So this represents the total number of electrons that you have in any given atom, which we refer to as atomic number. Okay. Okay. Let us look at the electronic configuration of carbon. For the electronic configuration of carbon, since we already agreed that we have the atomic number of carbon is 6, and therefore, if we want to write the graphical form of the electronic configuration, which is this here, this is the graphical form right here. Okay? When you want to fill the electrons in these orbitals, you start by filling the orbital of the lowest energy. So we say, okay, the 1s orbital will have a maximum of 2 electrons. We place 2 electrons there, right? And then we go to the next energy shell, second shell, the 2s orbital has 2 electrons. Okay? And then we have the 2p orbitals. Do we place 2 electrons on one of the 2p orbitals? No, we don't. Why not? Because they have the same energy. Anytime you have orbitals with the same energy, which we refer to as degenerate, No, that was meaning that these orbitals have the same energy. Anytime you have orbitals with the same energy, if you have to distribute electrons to them, before any one of them can get the full complement of 2 electrons, you must distribute all of those electrons to all of those orbitals. Then once each one of them gets 1 electron each, then you could then go back and fill the rest of them with the full complement of 2 electrons. In other words, in this case, we have 2s. We fill the 2s orbital with 2 electrons because it has lower energy than the p. Then the 3p orbitals, keep in mind the 3p orbitals, we place one here and the other one here. And that's what we've done here. So if I tell you to write the ground state electronic configuration of carbon, if I tell you to write the ground state electronic configuration of carbon, what is the first thing you have to do? The first thing you have to do, you ask yourself, what is the atomic number, right? You know that how many electrons does carbon have? That is the first thing you're going to ask yourself. Yes.
In terms of filling up the...
Is that Amco? Okay, go ahead. Oh, okay, yes, okay. What you are asking me is, okay, in this case, we have 1s, 1s2, right? 2s2, and then I say 2p x1, right? And then 2p y1. So you're asking, why don't you just say 2p2, right? Yeah. No, what I want you to do is to write it, place them in different orbitals so that we know with relation to the angular direction, the x, the y, and the z.
So if we were to assume that, let's say, something had 6 electrons, or so that's 7. So, well, actually 8 would work because it'd be 1s2, 2s2, 2s4. So it'd be 1s2, 2s2, 2x2, 2py1, 2p1.
Yes.
So it goes x, y, and z.
Yes. Okay. Okay, I want you to separate those orbitals because they are actually separate orbitals. Okay. So anyway, so this will be the ground state electronic configuration of our carbon atom. Now let us do a problem. Supposing I then ask you. Okay, let us pick. Let's pick phosphorus. No, let's do something else. Let's do nitrogen. Let's do nitrogen because I think I did phosphorus last year. Let's do nitrogen. All right? Let us do a ground state electronic configuration of nitrogen. Okay? So what is the first thing we need to know? Atomic number, right? And what does that give us? Number of electrons. Okay, so what is the atomic number of nitrogen? 7. Okay, so we have 7 electrons to work with, right? Okay, so we start with 1s, 2, then 2s, 2, so we have 3 more electrons to go, then 2p, x1, right? 2p, y1, 2p, z1. Okay, that will be the ground state electronic configuration of nitrogen. Now, if you want to write it in the graphical form, okay, this being energy here, okay, so that would be S, that's 1s, okay, and then we go to the 2s, and then we go to the P. Since there are 3 P's, okay, one here, and 1 here. Okay? Okay, so what we've done here is to write the ground state electronic configuration of nitrogen atom. Now, I bring this up because I want to also introduce another concept, which is very, very important. Yeah, you have a question? Yes, this will be the graphic one. Okay, graphic. Okay. Now, if you take a look at this ground state electronic configuration of nitrogen, take a look at the ground state electronic configuration of nitrogen. This part here, this here, those electrons are in the second shell, electronic shell, which will be this here. Those electrons are in the second electronic shell, okay? This here, because that is the last energy level that contains electrons, we refer to that as the valence shell. We refer to this as the valence shell or valence energy level. And we refer to the electrons in that valence energy level as valence electrons. So we refer to the electrons in that valence energy level as valence electrons. That is very important. In other words, these are the valence electrons right here. Because those electrons are contained in the second energy shell, and that is the last energy shell that contains electrons. Okay. So therefore, supposing we have let us write the ground state electronic configuration of oxygen. Ground state electronic configuration of oxygen. Okay. What is the atomic number of oxygen? 8. Did you say 8? Okay, good. Okay, so we start with 1s, 2, 2s, 2. So we've got 4 more to go, is that right? 2p, x, would that be, what will it be? 2, you say 2, very good. 2p, y, 1, good. And 2p, z, 1. So, how many valence electrons does oxygen have? How many valence electrons does, how many? 6, very good. 6, because those are the number of electrons in the last energy shell. Okay? Okay, so therefore, this will be the valence shell for oxygen, and therefore oxygen will have 6 valence electrons. Okay? About carbon. Carbon. What is the ground state electronic configuration of carbon? How many electrons does it have? What's the atomic number? What is it? 6. Very good. 1s, 2, 2s2, 2p, x1, right? 2p, y1. Is that correct? Okay, so how many valence electrons does carbon have? This is for carbon. 4. This is the valence shell for carbon. So therefore, carbon has 4 valence electrons. 4 valence electrons. Okay, 4 valence electrons. I keep coming back to this. It is very important because the next topic that we're going to deal with has to do with bonding. You are going to find that all of the bonding that is going to be taking place will take place with the valence electrons. And that's why I say this is very important. Okay, so carbon has 4 valence electrons. Okay? Okay, let us go back to okay, here, the ground state electronic configuration of phosphorus. See that? Okay, you either do the graphical representation or you do this representation here where you simply just write it out. Okay. Okay, we did oxygen already. Say atomic number is 8, the valence electron is 6. We've done carbon. Of course, hydrogen, the valence electron for hydrogen is only 1, right? Now, that takes us to the next concept, which we call the valence bond theory. These are one of the fundamental theories that underlies most of what we do in organic chemistry. At least one of those theories. The valence bond theory. Now, what does the valence bond theory say? Let me see. Do I remember somebody's name here? English. Yeah, go ahead. Can you read for all this part? I can hardly hear you. Okay. Okay, it says the valence bond theory, of course. Here it says only valence electrons are used in bonding. That's very important. Only valence, according to the valence bond theory, says only valence electrons are used in bonding. Keep that in mind. And therefore, you have two major types of bonding in organic chemistry. We have what we call the ionic bond, and then we have what we call the covalent bond. Ionic bond is not as prevalent as the covalent bond, but we do have to let you know that there are some organic molecules that who actually have ionic bonding. Now, an example of ionic bonding, of course, I would like to show you. I know all of you know this here, sodium chloride, right? It's not an organic molecule, but it would be a good example to show you what we mean by ionic bonding. Sodium chloride, that is your table salt. If you look at sodium, how many valence electrons does sodium have?
1.
1. Very good. Sodium has only 1 valence electron. Okay? So let us go ahead and depict sodium just as this. We show only the valence electron. How many valence electrons does chlorine have? 7. Very good. So let us depict that as this. Seven. Now see what is going to happen. In the case of ionic bonding, sodium, what does it do? It gives 1 electron to chlorine, and then what happens? You now have, what happens to sodium? Does it have a charge? No, keep in mind I say it gives 1 electron to chlorine. Remember at the beginning we showed you the atom, right? Okay. So the sodium is giving 1 electron to chlorine. So what is going to happen to sodium? Become positively charged, right? Okay, so sodium now becomes this. Become positively charged. Now what is going to happen to the charge on chlorine? Becomes negatively charged because it has received 1 electron. So that now it has 1 more electron more than the proton, right? So that becomes negatively charged. Okay, so now we have this. So become negatively charged. Now those two species, the sodium ion and the chloride ion, are held together by electrostatic attraction. Okay, and that is what we call ionic bonding. In other words, you now have them in form of ions. They are held together because of that electrostatic attraction. That is ionic bonding, in which one atom has completely given away its electron and the other atom has accepted that electron. Okay. So this is the case of ionic bonding. So that is one type, that is one extreme of bonding. Now we also have what we call covalent bonding. So this would be ionic bonding right here. Let us now take a look at the covalent bonding. Let us look at the case of this carbon here, right? And you have hydrogen here, hydrogen here, hydrogen here, hydrogen here. Okay. How many valence electrons does hydrogen have? 1. Okay, so we place 1, 1, 1, 1. Keep in mind, according to the valence bond theory, only the valence electrons take part in bonding. How many valence electrons does carbon have? 4. Okay? Now what is now going to happen? What happened now? The carbon and the hydrogen atoms, they come close together. They come close together, close enough to now form, each hydrogen atom will form a bond with the carbon atom. So, okay, so keep in mind now that this orbital here, you have orbital here, and an s orbital here, some orbital here, joining together without forming a bond. So now what do we have? We now have this. Okay, we now form a bond. The molecule we call methane. Now look at what has happened. If we look at this carbon atom here, look at how many electrons surround this carbon atom in this molecule. How many electrons? How many electrons? 8. 8. You have 8 electrons surrounding 8 electrons surround carbon in methane, right? 8 electrons surround carbon in methane. And then the question that we want to ask ourselves is, why do atoms bond? Why do they like to form bonds? Why do they want to form bonds? The octet rule, yes, that is correct. That's exactly where I'm going. But they do want to form bonds because the resulting molecules are more stable than the individual atoms. Okay, this is because of stability. Okay, then the question is, why are they stable when they form bonds? They are stable when they form bonds because they have a completely filled electronic energy level. In this case, they have 8 electrons, particularly those elements in the second row that we are going to be dealing with. We find that when they form bonds, they have 8 electrons surrounding them. So therefore, we have what we call the octet rule. In other words, for any molecule, for any atom to form a bond, a stable bond, particularly those in the second row of the periodic table, they need 8 electrons to surround them. And that is why we therefore call this the octet rule. Okay? The same thing happens if you go back to what I gave you earlier. In the case of sodium and chloride, what happened to sodium? Sodium has lost electron and chloride gain electron. What does chloride have? Chloride has 8 electrons surrounding it. But what about sodium? Does it have 8 electrons? Yes, it does. Because once you remove 1 electron from sodium, it now has 8 electrons surrounding it. So the reason why atoms want to form bonds, because they want to be more stable. And that stability sometimes is a result of having an octet of electrons surrounding them. Okay? And that is why we therefore have the octet rule. Let me see here. I see some of you already. Oh, okay. I see why. Okay. Okay, so let me just make this point and then we call it a day. So now we finish up with the octet rule. Okay. Okay. So the octet rule simply says atoms will do anything in order to attain an octet of electrons. Okay? They will steal electrons, they will gain electrons, they will share electrons in order to do that. In the case of carbon, carbon is sharing electrons. And that is why the sharing of electrons gives you the covalent bond. Okay? In the case of sodium and chlorine, sodium is giving electron and chlorine is accepting electron. In that case, that's ionic bonding. So in the case of covalent bonding, you have a sharing of bonding electrons. Okay, so when we come back, we are going to continue on this. By the way, I will not be in on Thursday. So what I want you to do, this Thursday. I want you to watch this second lecture that is posted in Blackboard. That is continuation of this lecture. The second one, for those of you who have seen the first one, you don't have to see the first one again. What the second one? That will be the second lecture that I'm supposed to give on Thursday. On Tuesday, there will be a short 10-minute quiz. On Tuesday, there will be a short 10-minute quiz. So I will see you next Tuesday. So you don't have to come in here on Thursday. Just make sure you watch that 90 minutes video. Please do that.